this as per usual, and I will bring up my iPad. There it is. All right, there it is. All right. Okay, so we have been talking about diffusion. Oh, diffusion. Okay, and so what we've described is that we started out thinking about diffusion in terms of the microscopic behavior of a collection of solute particles that are suspended in some solvent, say water or whatever. Okay, and so these particles undergo Brownian motion as a result of the repeated collisions between the solute and the solvent particles, so Brownian motion. And we modeled this Brownian motion mathematically as a random walk. Okay, and it's a random walk of individual particles, and so what we're doing is we're looking at what's happening on the microscopic scale. Okay, so now what we did last lecture was we said that if we look at any individual particle, we can describe what its position is at some given time, t plus delta t, as equal to whatever its initial position is, x at times t, plus some random step that it takes at that time. So this is its original position. This is the random step that it takes. And this is its final position. Okay, now we also said, so this step here, these steps are random. So you're at a position, the step that you take is going to be random, and it's going to be random in its direction, and also, I mean, as far as the formalism that we laid out, it in principle can also be random in length. All right, and so now the type of step that you take is completely random, and what we do is we essentially have a distribution of possible steps, and at each time point we pick one of those possible steps from our distribution randomly. Okay, and so these steps are described by some distribution of possible steps, which is what we call P of L. Okay, and so what we said was that if we're interested in looking at probability distribution of where a random walker can wind up, we said, so this probability distribution of the location of these random walkers, that's what we called rho. Okay, and we said that the probability to find a random walker at position x and at time t plus delta t is equal to its probability to be at some original position x prime at some earlier time t times the probability that the step that it took us from x prime to x prime to x, like so. And then what we had to do was to integrate over all possible starting positions, x prime. All right, and so this is what we came up with last lecture. And we said, now we made a few assumptions. We assumed that there was no drift and that the mean of this distribution, so the mean, or essentially the center of our probability distribution, so the mean of rho, which we would call mu, is at x equals 0. We also said that the width of the distribution is quantified by some standard deviation, which we called sigma. And we also said that the typical length scale of our distribution rho, that is the length scale over which rho changes appreciably, is much larger than the step sizes. Okay, so in other words, the scale over which rho changes is much larger than our typical step sizes, L. Okay, and so this is our continuum limit. All right, and so it's making this assumption, which takes us from our microscopic viewpoint of individual random walkers to a macroscopic understanding of what's happening over the larger length scales of the container that it's encased in. All right, and so by making this continuum limit, what that means is that this variable that we introduce, z, which is simply our step sizes, it's x minus x prime, that is the step sizes between our original and our final positions. So this is very small. And hence, what we can do is Taylor expand some of the quantities in this integral up here. And so when we apply these assumptions and we perform this Taylor expansion, I showed you that what we wind up getting is a differential equation. And so that differential equation that we get was this: the partial time derivative of the concentration gradient or the probability distribution is equal to a constant, big D, which we called the diffusion constant, times the second derivative of the probability distribution or the concentration distribution with respect to space. Okay, and this diffusion constant came out to be equal to the standard deviation of our distribution divided by 2 delta t, where delta t is the time interval between steps. Okay, so now, so this is the diffusion equation. This is where we wound up with on Wednesday. And now, before we go any further, I want to say a few things about this. So first of all, the way that we derive this, and our definition of the diffusion constant in particular, we derive this in one dimension. Okay, so all we're talking about is things diffusing along the x dimension. In higher dimensions, this equation looks a little bit different. All right, and so in higher dimensions, well, I mean, it's still the same. It's just written in different notation. So in higher dimensions, you can generally write this in the following way. It would be the time derivative of your concentration gradient is equal to the diffusion constant times the Laplacian of the concentration gradient. Okay, and then the Laplacian is simply a sum of second derivatives with respect to each of your spatial dimensions. Okay, so if, in other words, in one dimension, the Laplacian is just d squared dx squared. In 2D, the Laplacian is d squared dx squared plus d squared dy squared, and so on and so forth. Okay, and another thing that happens, you can see, so let me write it out for 3D as well. So in 3 dimensions, the Laplacian is equal to d squared dx squared plus d squared dy squared plus d squared dz squared. All right, and so now what's happening is as you go up in the number of dimensions, the number of terms in your Laplacian increases by 1. So I go from 1 dimension to 2 dimensions, I get a second term in my Laplacian. And so now it turns out that the fact that you get extra terms in your Laplacian also is going to affect your definition of the diffusion constant. All right, so essentially what's going to happen is for every term in the Laplacian, so again, let me write it out in one dimension first. Our diffusion constant here was sigma squared over 2 delta t. And essentially, this constant that I get out here multiplying the diffusion, multiplying the Laplacian, I'm going to get a factor of this sigma squared over 2 delta t for each term. All right, so in other words, what's going to wind up happening is that my diffusion constant in 2 dimensions is going to be sigma squared over 4 delta t, because I've got the 2 delta t coming from each of these guys. And in 3 dimensions, again, I'm going to get a sigma squared over 2 delta t from each term, and so my diffusion constant in 3 dimensions will be sigma squared over 6 delta t. Okay, so in general, in d dimensions, the diffusion constant is going to be equal to sigma squared over 2 times your number of dimensions times the time interval between steps. Okay, but I mean, otherwise it's the reasoning is exactly the same. Okay, so that's how you generalize to higher dimensions. Now, let's talk a little bit more about what the hell this thing means. All right, so let me again just write it down in one dimension. Okay, so what the hell does this mean? So again, this is just a constant. So who cares about that? This side of the equation, the left side of the equation, this is a rate, right? This is the d rho dt, this is a rate. So this is the rate at which your concentration gradient rho changes. Okay. On the right-hand side, the only other thing we've got over here is the second derivative with respect to position. All right, so now on Wednesday, we briefly discussed derivatives, and somebody pointed out that the first derivative with respect to position, what that tells you is slope of tangent lines, right? Somebody said tangent. So what the first derivative tells you geometrically would be the slope of a rho at any given point in space. But now this is the second derivative. So does anybody remember geometrically what the second derivative tells you about a function? Anybody?
Concavity.
Concavity, yes, spectacular. All right, so this tells you concavity. Or another way to put it, which I think is maybe a bit more intuitive, another way to state this is the curvature. All right, so in other words, the rate at which the concentration gradient changes is proportional to the curvature. The higher the curvature, the faster it's going to change. All right, so in other words, if I, again, draw what my concentration gradient looks like as a function of position, something which has really high curvature is going to be very sharply peaked, right? So a function that looks like this generally speaking has a higher curvature than a function that looks like this, that is less sharply peaked, right? So this has low curvature, whereas this blue function has high curvature. Okay, and in general, different locations on the curve, the rate at which the concentration at those locations changes is going to be proportional to its amount of curvature. So in other words, this blue curve here that's very sharply peaked, it's very rapidly going to spread out. And as it spreads out, its curvature is going to decrease, and therefore that process is going to slow down. Okay, does that make sense? All right, so in other words, what is driving diffusion is local spatial inhomogeneity in the concentration, because the more inhomogeneous it is, the higher the curvature, and therefore the faster it's going to diffuse. The lower the inhomogeneity, that is, the more homogeneous the thing is, the less curvature there's going to be in this function, and therefore the slower it's going to change. All right, and so in other words, a curvature or spatial inhomogeneity is what drives diffusion. All right, so now let's look at what happens in the steady state. So if you just let this process go forever to the point where the system reaches equilibrium, it's gonna reach a steady state. All right, so let's look at what the steady state looks like. Okay, so the steady state, by definition, as the name implies, is the state at which things are no longer changing in time. All right, so in other words, the steady state implies that the concentration gradient is no longer changing in time. That is, if we look at the time derivative of the concentration gradient, that's going to be equal to 0. That's the definition of steady state. Steady, nice and steady, right? Okay, so in other words, we take our diffusion equation and we set it equal to 0. Okay, so in other words, what this says is that d squared d rho dx squared is equal to 0. In other words, at the steady state where the time derivative is equal to 0, that means that the curvature is also equal to 0. Okay, so in other words, the steady state in a system like this, which is enclosed and isolated from the outside world, eventually it's going, you start out with some highly peak function and it's going to start to diffuse and spread out. And the final steady state is when the thing is perfectly flat. Okay, so it's flat, or in other words, homogeneous. All right, so you start out with a really localized distribution of dye. You inject something at a specific point in space. What this equation says is that it's going to rapidly start to expand and spread out and fill the space. And it's going to do so until the concentration of that stuff is the same at every point, everywhere. All right, does that make sense? All right, cool. So now what we're going to do today, beyond that, is we're going to come back up here. So these are the assumptions under which we derived this diffusion equation. And what we're going to do today is relax one of those assumptions. Specifically, we're going to look at what happens when there is drift, okay? So as an example of a situation in which you would get drift would be something like the following. All right, so again, let's say we have a container. And into this container, we squirt, so say right here in the middle of the thing, we squirt a bunch of molecules. All right, so whether that's dye or gas or whatever it is, okay? All right, so now what we're gonna do this time that is different than last time is we're gonna assume that these particles have some electrical charge. So assume these guys are electrically charged. So they're charged particles with charge Q on them. And then what we're going to do is we are going to apply an electric field. Okay. Now, you guys know that if I have charged particles and I put them in an electric field, they are going to feel a force, and that force is equal to their charge times the magnitude of the electric field. And so in other words, if these particles are positively charged, what you're going to get is a general force pushing them in this direction. If they're negatively charged, then it'll just push them in the opposite direction. All right, and so essentially what's going to happen in this case is that the particles are still going to diffuse, but as they diffuse, there's also going to be a force that's causing the whole collection to drift in one direction. All right, does that make sense? All right. So the way that we're going to describe this is the following. All right, so what we said before was that we had particles and we could describe their position at some time, t plus delta t. And we could describe this by what their previous position was at time t plus some random step at time t. And then what we're going to say is that there is just another term that's generally pushing their position in some direction. All right, so we're going to add on another term in order to account for this drift. And we're going to, the way we're going to structure this term is the following. So if we apply an external force, F, so there's my force. Now, how much that force changes their position depends upon the time step. So the stronger the force and the longer the time step, the more it's going to affect its position. So in other words, this term should also be proportional to delta t. And now the units here are not going to work out, right? Because F is going to have units of kilogram meters per second squared. Time has units of seconds. but we want this to give us position. So in order to make everything come out okay, we're going to multiply this by some constant, which I'm going to call gamma. Okay, so this is the previous position. This is the random step. And this is a external drift, or an external force term causing drift. All right. So now, first question you ask is, okay, gamma, what the hell is gamma? All right, so gamma is, again, it's just a constant. And this is what's referred to as the mobility. Okay, and we can determine what kind of units gamma has to have, because again, we know what we're doing is we're taking force times time times gamma, and that's giving us a position. And so if we look at the units of all these things, which I will indicate by drawing brackets around them. So the units of force are kilogram meters per second squared. The units of time are seconds. Gamma is what we're interested in. And we want this to come out giving us units of meters. All right, and so you can do all the algebraic massage, and what you can get is that gamma has units of seconds per kilogram. Okay, now another thing to notice is, again, we've got position is proportional, well, not proportional, that's the wrong way to put it. It is related, so in other words, I just want to ignore these first two terms. So in other words, I'm going to say that the position is related to this force times gamma times time. Right? Ignoring the other two terms. So now, again, if you look at this combination of force times gamma times the mobility, gamma, this must be some kind of speed, right? This has got to be some speed, because speed times time gives you distance or position. So in other words, force times mobility, F times gamma, is some speed, and this is going to be what we call the drift speed. Okay, is everybody with me so far?
Sir,
All right. Yeah, we have a question?
yes, question.
Yes.
Would the gamma be something like viscosity of substance?
It's something similar to that. Yeah, it's essentially a measure of how easy it is for these things to move around inside whatever the material is inside the container. So it's something like a viscosity. If you think of this, so you also encounter this kind of idea also when you think about electrical current. So in the context of electrical current, the mobility is something like resistivity, something like that. So yeah, resistivity, viscosity, it's that kind of idea.
Oh, okay, thank you.
Okay. All right. So any other questions? All right, good. So now what we want to do is to see how the introduction of a drift affects the diffusion equation. But now, before we do that, what I want to do is to go back to the diffusion equation without drift and essentially derive it in another way that is essentially going to make the application of drift much more intuitively straightforward. All right, so first of all, let's again go back to thinking about diffusion without drift. And I'm just going to essentially derive the diffusion equation in another way. All right, so here's what I'm going to do. So again, we're going to, one of the quantities of interest we're going to be interested in is this concentration, rho. All right, and it's going to be a function of position and a function of time. All right, so now this rho, again, is a concentration or a density, right? And in particular, the way that I'm going to define it in this context is as a number density. All right, so it's the number of particles that we have in a given volume. And in particular, we're going to look at it, first of all, in one dimension. All right, because one dimension is easy to think about. And so that's why here I've divided by delta x, because in one dimension, delta x is my volume. All right, so now one way to look, so let's look at this graphically. All right, so on the x-axis, that's going to be position. And on the y-axis is going to be concentration. And what I want to look at is the space between 2 points within my container. So I'm going to look at the point x, and I'm going to look at the point over here, x plus delta x. Okay, so in other words, the distance between these 2 points is just delta x. Now, what I want to know is if I look at the region between these 2 points, I want to know how many particles are in that region. Okay, so how many particles are in here? Well, so with this definition of rho, that's really straightforward. All you do is you just take whatever the concentration is, whatever rho is within that region. Okay, so whatever the concentration is within that region, and you just multiply it by the distance, right? So in other words, the area, I don't like black. Let's get some colors. Purple. Oh, yes. I feel like Prince today. There we go. All right. So the area of that rectangle is the number of particles within that volume. So N is equal to density times volume. Okay. Does that make sense? All right. So now what we want to do is to look at how that number changes. Okay, so in other words, we want to look at how N changes in time. Now, how is N going to change? It can only change in 2 ways. One is if you get flow of particles into that volume, and the other is if you get a flow of particles out of that volume. All right, so in other words, let's say we look at, how do I want to put this? So I want to look at the rate of flow, or in other words, the flux of particles into that volume. And I'm going to call that flux J, okay? So this blue line here, that is the flux into that volume. And this blue line over here, this is the flux out of that volume, okay? All right, so now what I can say is that if the number of particles changes, the rate at which the number of particles changes is going to be equal to the flux in minus the flux out. Whoops. Okay, so the rate at which it's changing is just equal to the flux in minus the flux out. Make sense? All right, very good. So now if I come back up here to this, so the number of particles is related to the density times my volume. So now if I just substitute this into here for N, then what I get is this. So it's the time derivative of rho times delta x. All right, so now the volume itself is not changing. The only thing that's going to be changing with time is the concentration profile within that volume. So in other words, when I take this derivative, I don't have to worry about taking the derivative of delta x. The only thing I have to take the time derivative of is rho. All right, so what I get is that j of x minus j of x plus delta x is equal to the time derivative of the concentration profile times the volume of my box. Okay. All right, now, oh, can you feel it? Can you feel it happening? Can you look at this and can you feel what's going to happen? If you can't, I mean, so I mean, look at this. What is this starting to look like to you? Again, this is starting to look like a derivative, right? Okay, so what I'm going to do is simply rearrange this equation to make this look even more like a derivative. So I'm going to reverse these two terms. So I'm going to say negative j of x plus delta x minus j of x. And then if I divide both sides by delta x, I get this. Delta x is equal to d rho dt. All right, so now all I do is I just take the limit as delta x goes to 0, and this thing over here turns into a partial space derivative, right? Because I mean that's the definition of a partial space derivative. So in other words, what we get is this. The time derivative of the concentration profile is equal to the negative spatial derivative of the flux. Okay. Cool. All right, so now let's compare this to our diffusion equation. Okay, so the diffusion equation looks like this. Whoops, no minus sign. D squared dx squared, like so. Well, these look awfully similar, yes? So what this tells me is that I can simply rewrite the diffusion equation like so, making the assumption that the diffusion constant is in fact a constant. So if I write the diffusion equation like this, and again, I compare this to what we just derived up here, thinking in terms of flux, what this tells me is that I can define this quantity called the diffusive flux. So the diffusive flux is equal to minus d rho dx. All right, make sense? Okay, so in other words, the flow of particles within this system, the flow of particles in and out of that volume is a consequence of diffusion. And you can quantify essentially the rate at which diffusion is happening by this flux. And the diffusive flux is just equal to minus diffusion constant times the spatial derivative of rho. All right, make sense? All right, cool. So now let's think about what happens if there is drift. What if there is drift? Okay, well, so again, and outside of the context with no drift, what we said was that this flow of particles into and out of this volume is just a consequence of the diffusion. Now, if we include drift, the flow of particles in and out of that volume is now going to be the result of two things happening. One is going to be diffusion, just as we had previously. And the other is going to be the drift, right? Because now the drift is also going to cause particles to flow in and out of that volume. Cool. So in other words, when there is drift, what we would say is that the total flux is going to be equal to our diffusive flux plus another flux coming from the drift. All right, so now the question is, what is the flux from the drift? Now, there's a variety of ways to think about this, I think. So now let's come back up here to this equation. All right. So we had that the number of particles within this volume is equal to the density times the volume, right? And then what we said was that the flux, So when we wrote this down right here, the flux is related to the rate of change of that number of particles. That is the definition of the flux, right? This says that the rate of change of the particles is the flux in minus the flux out. Okay, so J is related to the time derivative of the number of particles. Okay, so if I take the time derivative of the number of particles, this is equal to the time derivative of rho times delta x. All right, so now what I said previously was that the volume is not changing. All right, and so we only had to take the time derivative of the concentration profile. So I think another way to think about drift is not only is the concentration profile changing, but essentially what's happening is that you have some concentration profile, and what you're doing is looking at a volume as it moves along. So another way to think of drift is that you keep the concentration profile constant, and then the volume that you're looking at just scans across that concentration profile. Does that make sense? All right, so in other words, probably a more, so again, this is not precisely correct, but I think a good way to think about it is you could also write this as the rho dt delta x plus rho d delta x dt. Okay, so in other words, not only is the concentration profile changing, but so is essentially the volume that we're looking at is also moving as well. All right. So now notice this is a derivative of position with respect to time. In other words, this is a speed, right? This is a speed. Oh, look. Previously, when we talked about drift, oh, we encountered another speed. We encountered this drift speed, right? And so we said that if we have drift, the speed of the drift is equal to your magnitude of your external force times this mobility constant. All right. So in other words, from this argument, I know that my flux term should look something like the concentration profile times the speed. And hence, I am going to hypothesize that my drift flux is just equal to my concentration profile times the drift speed, which is equal to the concentration profile times the external force times the mobility. And now it turns out that that's correct. All right, so this is what we're going to use for the drift flux. All right, cool. All right, so now what we showed previously without drift was we showed that the time derivative of the concentration profile is equal to the negative spatial derivative of the flux. All right, and so now what we had previously was that this flux with no drift, this was just equal to our diffusive flux. With drift, then our total flux is equal to the diffusive flux plus the drift flux. All right, so in other words, this J here in this equation, this is, I'm going to say that this is the total flux. And so then what I'm going to do is to take this expression for the total flux and just take a spatial derivative. All right. So in other words, I get that d rho dt is equal to the negative derivative with respect to space of my diffusive flux plus my drift flux. And that, so my diffusive flux, as we showed earlier, is minus d rho dx. And my drift flux is rho f gamma. All right, now I'm going to assume that the applied external force is constant, so we're not going to make this any more complicated than we have to. So F is a constant. Gamma, as we described earlier, that's something like the viscosity or the resistivity or whatever you want to think of it in whatever context you're talking about. So in other words, the mobility is also a constant. So this is we're going to assume the applied external force is a constant, and the mobility, essentially by definition, is a constant. And so when I distribute this derivative through, the only thing, again, I have to take the derivative of is rho. All right, so what I get is this. d rho dt is equal to d squared rho dx squared. So that's exactly what we got previously from this term for diffusion. And now, with our applied external force, what we get is minus F gamma d rho dx. And let me make sure that I wrote that down correctly. I did indeed. All right, so now this is what we are after. So this is the one-dimensional drift diffusion equation. All right, so this is, it's the same thing as what we derived on Wednesday. So it's still the diffusion equation. It's just a little bit more general now because we have this additional term on it, which tells us how the thing will drift when an external force is applied.
Question?
Yes, please.
So if there are different forces acting on the drift,
Yeah.
would the gamma still be the same for all of them?
That's a good question. I suspect the answer to that is no. I think that the definition of the gamma is going to depend upon, well, is that going to be true?
Because if we were thinking about it as viscosity or resistance, the direction wouldn't
I think it
change.
doesn't matter. I think whatever the force is, you just plug in the magnitude of the force into this equation, and this is what you're going to get. So regardless of whether the force is coming from an electric field or a magnetic field or God knows what, all you do is you just plug in the magnitude there, and it'll give you the right answer.
All right, thank you.
Yeah, so in other words, the gamma does not depend upon the type of force. Now, if you encounter this again in like electromagnetism, their definition of the mobility of electron charge carriers is probably going to be a little bit different than this. And in that case, the units of the electronic mobility may be somewhat different, and then it may matter. But at least with this definition of the mobility, doesn't matter. Okay? Okay, so now let's think about what this means. Okay, so what we have is now, so we talked at the beginning of the lecture about what this term means, right? So what this term says is that the rate of change of the concentration profile depends upon how sharply curved it is, or what the concavity is. All right, so now let's talk about what this new term does. So now this is the first derivative of the concentration profile with respect to position. So this is related to the slope. All right, so this term here is the curvature, and the second term is the slope. All right, so now what does that mean? So what this says is that if we have, so under an applied external force, so under an applied force, we get this additional term. So we get a term that looks like this, minus gamma F d rho dx. Okay. So let's assume that our force is in the positive direction. Okay, so whatever's happening, let's assume that our force is positive. Okay, And let's say again, draw an example concentration profile. So let's say this is position and the y-axis is concentration. And let's say that we have something that looks like this, just for example. Okay, so low concentration over here and high concentration over here. All right. And again, what we're doing is we are applying a force in the positive direction, we're assuming. So the force is going this way. All right. Now, so what this term says is that this term is going to drive the change in the concentration profile coming from this force. Okay, so in other words, if we look at some position, let me do that with black. So let's say we look at this position right here, X. And we come up here to this point. Okay, then what we want to do to determine how the concentration profile changes at that point due to the applied external force is we look at the slope at that point. Okay, so the slope at this point is positive. All right, so we have a positive force being applied. We have a positive slope of our concentration profile. And then because of this minus sign, what this says is that as a consequence of this, the change in the concentration profile with respect to time is going to be negative. So in other words, what we expect to happen to the concentration at this point with this arrangement, we expect the concentration to go down. Now, why is that the case? So essentially what's happening is that this applied force is acting upon this concentration profile that I've drawn here and essentially just pushing the thing in the direction of the force. All right, so in other words, what's happening is that, again, if I draw this again, and we start out with this concentration profile, and the force is being applied this way, then what is happening is that this concentration profile is just drifting in the direction of the force. So at some later time, it's going to look, that's a bad choice. Some later time, it's going to look like, it's just going to drift to the right, like this. And then an even later time, it's going to be drifted even further to the right, like this. And so what you can see is that if you look at the concentration at this point, as this curve moves to the right, essentially what's going to happen is that that value is going to migrate down that curve. That is, it's going to decrease. All right. So in other words, the drift is just pushing the concentration profile in the direction of the applied force. And then as a result, the concentration profile is changing in exactly the way that you would expect it to from that. Okay. Does that make sense? Yep. All right. So I think that is essentially everything I had planned to talk about today. And so now what we've done, again, just to summarize, is we started out thinking about the motion of individual molecules in terms of a stochastic random process, that is a random walk, by expanding our minds and going from individual microscopic description of an individual particle to a macroscopic collective description of a collection of particles. What we have seen is that this microscopic stochastic process results in the emergence of a macroscopic deterministic phenomenon, that is diffusion. Okay, and we were able to write down a differential equation, which given a concentration profile is just like Newton's laws. So just like Newton's laws allow you to, are differential equations that allow you to predict the trajectory of a particle through space, what the diffusion equation is a differential equation which allows you, given a concentration profile at some time, the diffusion equation tells you how that concentration profile is going to evolve through time, either as a consequence of diffusion or an applied external force. So in other words, we went from the stochastic process to a deterministic emergent phenomenon described by a deterministic differential equation. So it's magic. All right, so that is an example of what's going to happen with statistical mechanics. So now what we're going to do starting next week is what you really think of when you think of statistical mechanics. We're going to start talking about things like the behavior of gases and really partition functions, all this kind of good stuff. So we're going to start getting even more hardcore about this next week. All right, so any questions?
I have a question.
Yes.
On the last lecture regarding scale invariance.
Yes.
Is scale invariance basically saying that the macro is the same no matter how big we scale it?
Yeah, essentially. So I decided not to talk about that in the lecture because I didn't think it was super obvious from the material that we covered. But the idea is that what happens is you look at the average behavior of these particles, and what you get is that on average they expand to some blob whose radius is proportional to the square root of number of steps that they take. All right. And so now you can scale up or scale down the size of the steps. That is, you can make L bigger or smaller. And yet still the shape of that thing is going to remain the same. It's still going to only depend upon the number of steps that you take. Okay, so in other words, like the jaggedness or the how random it looks doesn't matter on this, or doesn't depend on the scale at which you choose to look at it. But again, I didn't feel like the material that I presented in the lecture was really made that point obvious, and so I didn't want to belabor it as much as I.
Well, I kind of see where it's going, and so I do see where it's coming from. Where once you get to the macro scale, it doesn't matter how you scale it, since it's all statistics, then it should scale the same.
That's exactly right. Yes, that's the idea.
And then for the opposite is the universality that you also mentioned. That would be how it's independent of the micro, right?
That's right, exactly. That's right. So the answer that we get didn't depend upon the step size that we took. It didn't depend upon the size of the container. And it didn't depend upon the mass of the particles. So the analysis that we did, it could have been any kind of particles, and you'd still observe the same kind of behavior. So that's universality.
Thank you.
Yep. All right. So with that, have a good weekend. And I will see you guys again on Monday. Adios.